before Pavel, you will start as I present Uriel, let me also present you. Pavel Yosifevich is a trainer and also, of course, the co-founder with Uriel of trainsec.net. He's a developer and also an author. He wrote several books, many books, not just related to security, also programming, Windows 10 system programming. And as I mentioned, he's offering recorded classes in Windows, internals, and low-level programming, although he's also a cybersecurity professional. So as Uriel mentioned, he's the true bad guy, okay? Because he knows the two sides of the coins. Now I understand, Uriel. Okay, so as I mentioned, he's also author of many books. I cannot count them all, but many. He's also teaches various classes related to low-level software development, and he's broadcasting from New Jersey. So, Pavel, the stage is all yours.
Thank you, Lior, for that introduction. Not that many books, by the way, just about 5, 6, or 7. Anyway, what I'm going to do, I'm going to move to my other screen, so you won't be seeing me, but that's okay. It's not a big loss. The most important thing is my screen. So I want to present a few slides as well, and then go into some live coding. What I want to discuss first is the general approach that EDR take as they are architected and deployed on a typical Windows system. So we have this little red line that separates user mode from kernel mode. And on the kernel side of things, we have, of course, the kernel itself, which has these two pieces called executive and kernel, which I'm not going to discuss in detail. And then we have some kind of driver. And so EDR typically have a kernel driver whose purpose is to get information that is very difficult to get from user mode, or sometimes even impossible. And the purpose of this driver is to aggregate that information in some way and then send that for further processing to some user mode service, which is still part of the same EDR system that's supposed to get all these notifications and information, try to make sense of it, tries to make sense in a way to identify whether there's any malicious activity that is happening. And typically it also send information to some server for aggregating the information from multiple machines that might be part of the same domain or something like that. So this is kind of the basic EDR architecture. And what I want to focus here in this demonstration is on the kernel driver. What Uriel has shown is the idea of injecting a thread into a different process. We're using the create remote thread function. And so the idea here is that this is sometimes not necessarily malicious. There are some legitimate reasons for that. And maybe that's a good time to ask the audience. Lior, you want to do the honors of asking our question in a poll. What is the create remote thread should be used for? I mean, why is it even there? Why does it even exist? It seems to be like a function that could be problematic from a security perspective, so why does it even exist? So I'll let you ponder that a little bit. Lior, hopefully you're taking care of that part. And I'm going to continue with my presentation. So one thing to note is that when a process is being created, there's actually several steps for that. In fact, it's a pretty complex process, so to speak, to create a process. In any case, the important thing to note here is that some operations are happening on the creator process, that is the one that calls an API function like create process, because the new process is not there yet, so it has to start somewhere. So the creator is doing certain things, and some of the initialization eventually happens in the context of the new process once it's already running enough or exists in kind of enough state. So here's the main steps there. The first thing that is going to happen, the kernel is going to open the image file, that is the PE, to make sure that it is a true PE and it looks as a good PE to work with. And then it's going to create the kernel object representing the process. This is the e-process structure, some of you may be familiar with. So going to create that structure, initialize that properly. This is still all happening in the context of the creator process and the creator thread that called the create process API, for instance, from user mode. This, of course, all these things are happening within the kernel. Then there's also the first thread being created. And so when a process is created, normally a process object is created. Also, the thread object is created, which is going to be the first thread in the process, which eventually, if all goes well, will run the main function that you have in a typical application. So the important point here to note is that the first thread in any process is always a remote thread because it is created by a different process, which means that if we want to somehow know whether a thread being created is a remote thread or not, we can't just compare process IDs and see who is the creator and who is the process where the thread is being created. We also have to make sure it's not the first thread in a process, because if it's the first one, it's not really an injection over a new thread in a create remote thread kind of way, but it's just the normal way the things work. The first thread in every process is always technically a remote thread that has been created by a different process. That will complicate our code a little bit, maybe not that a little bit, in the driver I'm going to demonstrate very soon. And then there's some other stuff that is happening, such as mapping the image itself, the P image and NTDLL, into the address space of the newly created process. Then CSRSS, which is the Windows subsystem process, is the one that's helping kind of the kernel, helping the kernel to manage processes that belong to the Windows subsystem, which I'm not going to cover here. So it needs to get notified that these things have happened, that a process and a thread has been created. And only then the new process is live enough to execute some code. And the initial code is executed by the loader, which is part of NTDLL, which is a very fundamental DLL in Windows that every process must use, every user mode process must use. And this is mapped by the kernel, as we see on the left-hand side. And it performs some extra initialization in the context of the new process way before the actual main entry point is being called. So it creates a PB and TB and does some initialization, like creating a default process heap, and initializes some thread pool support and all that kind of stuff that needs to happen. Then it loads all the required DLLs, all the DLLs that are required to be used by the executable based on the import table that you find in the PE, that of course it reads the PE and sees what that executable needs, and it does so recursively because the DLL might need other DLLs, so it does these things recursively and loads all the required DLLs. If anything goes wrong and DLL is not found, for example, then the process will crash. You get a nasty message box and the process will crash because it can't properly initialize. Only if all these DLLs are loaded correctly and successfully and they have the initialization function called and returning true, only then the actual entry point of the executable is being invoked. And by the way, this is not typically your main function that we write as say C or C++ developers. It's actually the C runtime entry point. And there's a reason for that, which I'm not going to discuss. It's not really in scope of what we're trying to do here. So the thing here to remember is that the first thread in every process is always technically a remote thread, so we have to make sure we don't like stumble on that little issue when trying to detect a remote thread. So let's see what that might look like. So I have here a code very similar to what Uriel has shown that performs an injection just for testing purposes. This code performs an injection of a thread using the create remote thread function, just like Uriel shown. However, instead of injecting shellcode, what I have here is the ability to load a DLL that's being passed as a parameter to this executable on the command line. You specify the process ID that you'd like to inject into and the path of a DLL, and that is going to happen. And so the way this works, many of you are probably familiar with this technique of loading a DLL or forcing another process to load a DLL of your choosing, is by using create remote thread and having the thread function being the load library function. And so since the load library function and the thread function have the same binary signature, they all accept a pointer and return whatever, which doesn't really matter, then what would happen if I put the path of the DLL into the target process by allocating memory and copying that path into the target process, it will call load library in the context of that new remote thread that will load my DLL, whatever malicious DLL I might want to load. And of course, in this example, I have a very simple DLL here that has the name simple DLL, just to make sure. And what that DLL does basically is just using the message box function here in the DLL main function when the DLL is loaded, and shows that it has been injected into a process given by the current process ID. So that's what we have here, just as a way to test whether the thread was properly injected and DLL was properly loaded. So we have the poll there. Let's see what the poll has to say. What is the reason for the existence of create remote thread function? And so the answer, the correct answer is answer number 3, which is to allow debuggers to break into processes. So the thing is, let's say we have a process that is currently running and I want to attach a debugger to it. When I attach a debugger, I'd like it to be broken into. So how can the debugger actually do that? And the way it does that is by using create remote thread and injecting a thread into the target process that calls the dbg breakpoint function. And then this is exactly what you get. So here's a simple example just to prove that I'm not making this thing up. Here's a little notepad process here. And I'm going to launch a debugger. I'm going to use WinDebug here to make it a bit more fun. So here's my WinDebug here, and I want to attach this notepad process. I'm going to use attach to process here. I'm going to find notepad. Here's notepad and use attach. And we should attach to the process, and we do. And if I take a look at the call stack of the thread that we just broken into, you can see that the function here is dbg breakpoint, and that was actually a thread that was injected into the target process, into this notepad process. It didn't exist before I made this attachment. So that is the true reason why create remote thread exists. We need to have that kind of function, at least for use in debuggers. But as like any other function, it has its uses and it has its abuses. It's always possible to abuse almost anything, and this is the case here where we use create remote thread for a different purpose. So we'll see that when we try to detect remote thread injection, we'll detect even these kinds of cases where we have a normal debugger attached, which is not a malicious thing on into itself. So this is the part where the EDR has to invoke some kind of logic to figure out whether this is a malicious intent or not. And that's going to be beyond the scope of what I'm trying to do here. What I'm going to do here is just to show you how we can, using a kernel driver, to have that kind of power to figure out remote threads when they actually get created. Okay, so let's see how we're going to do that. First, we have this application, a DLL, for testing purposes. What I want to do is use a kernel driver here. And the reason I'm using kernel driver is, well, first, it's probably more interesting and something that many of you probably never have seen. And the second reason is that you can always have more power when working within the kernel. You can also identify thread injections from user mode, for example, by using event tracing for Windows or ETW. However, with ETW, what you get is some delay between the time the event happens and the time you get notification, which is roughly between 1 and 3 seconds typically. It depends on the size of buffers you configure for ETW. And the problem is that if you have a short-lived process that injects something and then goes away, then you've missed that process. Although you do get some injection information, the original process is gone, the injector is already gone. So if you try to open a handle to it, you can't. And on the other hand, in the kernel, everything happens in line. That is while the thread is being created. So at that point, you have all the powers to check more about this thread and the original process and things like that. So you generally have more power when working on the kernel side of things, which is probably what we expect. So this is what I want to try to do here. Now, obviously, if you've never seen any kind of kernel code, some of these things might seem a bit complex. I'll try to make it as simple as I possibly can. I'll try to explain everything that I'm doing in a good enough way, hopefully. We'll see. If you do have some kernel programming experience, that this will be much easier for you to understand. So let's go ahead and add another project to this solution. And I want to create a driver project. So I'm going to have this, there's this template called empty WDM driver. We can search for it, but I already have it, have that one pinned here. I'm going to select that. Now, if you want to try that later yourself, it's important to realize that you need to install the Windows driver kit for that. You can do that through Visual Studio, in fact, today, or separately. So you have that template available to you, as it's going to be installed as part of Visual Studio as part of that extension. And so I'm going to call this KDetect detector, just a name, or KDetect to make it shorter. I'm going to use create here. What that does, as a template suggests, it's supposed to create me an empty project. So it is almost empty. There's just one file here, which is an INF file, which is the bare bones that we need to install a driver using an INF file. But for software kind of drivers like the one we're going to write, using an INF file is not really required. So I'm going to just remove it just by deleting it, delete it entirely. And now we have a truly empty project. So it might seem kind of pointless, what would we do with an empty project? But the important point is that all the settings for the compiler and linker to build a driver are in place. So I'm going to use that as a starting point by adding a new item here, some C++ file. Let's call that kdetect.cpp and start writing our driver. The first thing to do is to add an include. So just like if you've done any user mode programming and you include windows.h to get support for most of the Windows APIs, now you have to use a different include. The ntdk.h is kind of the basic one that provides access to most of the kernel API that you get from the Windows driver kit. And then you have a function called driver entry. Driver entry is the function that is the main function of the driver. Just like normal applications have a main function, drivers have their own main function, and classically it's called driver entry. And of course, just like the normal main function that you're familiar with from user mode, for example, there's a certain prototype here. So we get here two parameters. One of them is a pointer to a driver object. The driver object is the kernel object that represents our driver. It's being created by the kernel and handed over to us here in this function. And then there's another parameter of type pointer to a Unicode string, which is a way to represent strings in the kernel, typically called registry path, that provides the registry key where our driver is installed. And we'll see later how to install the driver, and we'll see that it has to be written in a certain key in the registry. So this provides that path, which is useful for drivers to store configuration information, things like that. We're not going to use it, so I'm going to just remove it to not have that particular name. If I do hold on to that name, we'll get like weird warnings, because if we try to build it now, it's going to give me a warning saying that unreferenced formal parameter. There's parameters here which I haven't touched, which means that the compiler is not happy. It's configured to the most strict warning level, and there's another setting here that says treat warnings as errors. So it actually is not going to compile because of that. So one way to deal with that is use the macro unreferenced parameter, which paradoxically actually references the parameter just with a semicolon. So it makes the compiler happy. Or you can just remove the actual parameter name, which is okay to do in C++. Okay, so what do we need to do here? What do we really want to do? In order to detect a remote thread, we'd like to know when a new process gets created and when a new thread gets created. And the kernel is nice enough to provide two callbacks we can register for that's going to be called when such an event occurs. So the first one is called psset create process thread notify routine ex. That's the function that says I would like to register a handler, a callback function, to when a process gets created or destroyed. I need to give it a function name. Let's call that onProcessNotify. And there's a Boolean indicating whether I'd like to register or unregister. I want to register, so false here is the parameter to use. And that's going to return a status for me. And the status is of type empty status. Let me be more explicit about it, which is the normal way to report errors from kernel APIs. And generally 0 means success and negative numbers mean some kind of error. So of course I'll have to write this function properly, but if this doesn't work, and there's a anti-success macro here we can utilize that just checks to see whether this thing is 0 or a negative value, and if it is a negative value, there's really nothing we can do. We can just bail out and say error registering for process notification. So we can have this this function called dbgprint, which we'll be able to see in various tools like the kernel debugger or some other tool that is going to just pop up this message to give us some indication as to what went wrong. That's probably the simplest thing we can do. And we can bail out and say, okay, we're done if we can't get this to work. Why would that even fail? It seems to be kind of weird. And one reason it could fail is because there's only this list of callbacks for process creation destruction is limited to 64 callbacks only. So if you happen to have many drivers on your system that register for this same callback and 64 of them already have registered, then you can't register any more callbacks for that. This is fairly rare, but still technically could happen. So it's always important to make these checks because we know that anything bad happening in the kernel, if we don't properly check for it, we'll get the nasty blue screen. We'll try to avoid that at least if we can. So now we need to write this onProcessNotify function. I can go to the documentation for that, but we can also use F12 to get to the definition. We can see what that function looks like. I'm going to just do some copy pasting here, write it here and say, here's the function. I'm going to call it onProcessNotify. And I have here the parameters, so that's going to be fine. And we'll deal with the implementation very soon. The second thing I need to do is to register for thread notifications because we want to identify threads that are remote created. So anytime a thread is created, we need to know about it. So we're going to do exactly the same thing, but this time using a different function called ps set create thread notify routine. That's a different API. And again, let's call that onThread notify. It's going to look different in a different way, but we're going to just try to get that notification call back. If that doesn't work for whatever reason, again, nothing much we can do here. I'm going to do the simple thing here to unregister the process creation routine so we don't leak and a driver will not be maintained in memory for no good reason. And again, we can return status here. So basically, once we do these two things, we're done with what I want to do here. I'm going to write code to report the information to user mode. That will just take too much time. I just want to write something that would allow me to detect this eventuality. What about onThread notify? How would that function look like? Again, I'm going to press F12 here, and we can see the type def right here. I'm going to just grab it and put it right here. And again, give it the name that I want, which is onThread notify, like so. And that's good enough for now. We have the prototype of the function. The last thing to do before we can return status success finally to the kernel indicating loading of the driver is successful is to provide the opposite of driver entry. So there's a question here, can we know how many drivers have registered for process creation? The answer is no. There's no way, no official way to know that. It's just something that you try to register your callback. If it works, great. If it doesn't, then kind of your problem. Okay, so the last thing I need to do is to have some function that's going to be invoked when the driver is unloaded so we can properly unregister all that stuff. And the way to do that is to go to the driver object. There's a driver unload member there. I'm going to call that onUnload to define an unload function. An unload function looks like this. It's all documented, of course. I'm just saving some time here. It expects a driver object. And that's it. It returns nothing. So we can implement that very quickly by using control dot and just creating a CPP, just the actual function, having Visual Studio a little bit helping me here. And what we need to do is to unregister what we've registered. So I'm going to remove the process notification routine by specifying true here as the the flag to say to remove. And for the thread stuff, there's the opposite function, ps remove something, set create. We have the thread, and there's also the remove function. So just it's not symmetrical, which I think is pretty annoying. So we probably need to figure out what the function is, but that's ps remove something. Thread notify routine. Okay, so I'm going to give my own thread notify here, and we're done in that sense. If we build that, we should have the code compiling, but it doesn't link properly. It doesn't link properly because we have two functions we haven't really implemented. So obviously we need to do something about that. So now comes the more interesting part. How do we actually do the detection? So remember, the problem is that when a new thread is created, we probably want to compare the creating process with the target process where the thread is supposed to be created. If they're not the same, it's a remote thread. That's almost true, as we've seen. And one of the problems is that the first thread in every process is always a remote thread. So we have to be careful here. Otherwise, we're going to report things which are just not correct. And so let's go ahead and start with the on-process notify callback here. I'm going to use control dot again to add the implementation here. You can see, of course, there's nothing at this point. So what do we get in this process notification function? We have the process object that is being created or destroyed. That's the pointer to the eProcess structure maintained by the kernel representing this process. By the way, if you want to dig into that and look into the members of the eProcess, you get nothing. So it's actually typed as a void star, a pointer to void. And the reason is that this structure is not really documented, and for good reason. Sometimes the members there change or being added or change positions. So Microsoft doesn't want anyone taking any dependency on that information. Although the information is available when you're debugging a certain system, because for a certain system you get symbols and you get the correct eProcess structure members, but in general you can't use any of that. So if I try to do like process error or something, I get nothing. There's really nothing there. But certain APIs allow us to pass this opaque pointer to get some information. Then we have the process ID for the process being created or destroyed. So that's the process ID. And it looks a bit weird because the type seems to be a handle. So is it a handle or a process ID? And the answer is, it is a process ID. That's the unique ID, the same one you see in tools like Task Manager that represent this process uniquely in the system while the process is alive. But why is it typed as handle? And the reason is that the process and thread IDs are actually generated from a handle table behind the scenes, which is a global handle table maintained by the kernel. So the type is hand, but really it means an ID, which might be a bit confusing, but once you get the hang of it, you realize it's just the way it works. And then we have a pointer to a structure here that provides more information about the process being created. If the process is being destroyed, then create info here is going to be null, indicating its notification or process destruction. So I'm going to look at create info here. So if the process is being created, I'm interested. If it's being destroyed, I'm not really interested anymore because I don't care about that. And the reason I care about process creation is so I know that the next thing I expect is to have a thread creation in this process. If this is the case, I know it is not a true remote thread. It's a remote thread just because it's the first thread in the process. It's not something I want to detect. I want to just disregard that. So I need to know there's a new process coming along. So I have to add that to some kind of list I have to maintain to indicate that we have here a new process that has been created. And I'm also going to use a dbg print here to say that a new process was added to my list. And I'm going to display here the process ID by using the function handle to ulong here, which is a simple function that just casts the process ID as a handle to a simple number. So we can have a better way of just passing that as an unsigned long rather than a handle, which is basically a 64-bit pointer. It's not really a pointer, but it's typed as a pointer. And so, so this is what I want to do. I want to track these new processes. So once the first thread is created, I'm going to remove that from a list of processes. So it means I have to now manage a list of processes. And to make things as simple as I possibly can, I'm going to use a list of process IDs in a fixed array. So I can say new processes. I'm going to have a number of new processes. Let's just use some constant here, like max new processes. Let's use something like 16. So I can only handle 16 new processes before the first thread is created. So it should be enough, even more than enough. It means that if I have some crazy fast 16 or more than 16 processes being created at the same time, then I might miss a process because I won't be able to add it to this array. So of course we can just change that to any number basically. But in a more realistic scenario, probably would create something dynamic here. So I'm not dependent on the rate of process creation on a particular system. But again, for simplicity, I'm going to stick with the simplest thing I can get away with. And I'm going to also, of course, count how many current processes we have. So a new process count. And since these are all global variables, they're always initialized to 0, so everything is empty there. So we have an array here of zeros, and here the new process count is 0. And we want to write this function called add new process, whose purpose is to add the process ID to the list. And of course, we'll have a function to remove that as well. So we need a function to remove remove new process. And this is something we're going to do when we have the first thread in that process already created. We know that from that point on, we should treat any subsequent thread in that process, if it was created by a different process, as a true remote thread. Okay, so I'm going to just define them here, and then we need to do the actual work to add the processes. So let's go ahead and do that. So here's add new process. We have the process ID. We need to add it to the array. And of course, it might fail because the array, in a very maybe I would say corner case, might be even full. So we want to search for an index. So we have here the max new processes here we can use. And I want to search for an index of 0. And if we have an index of 0, we need to update that with the process ID. So I'm going to say if the new process ID is here at index I happens to be 0, it means this is an empty slot. Then we can utilize that by putting in this particular slot the process ID. Again, going to do handle to ulong here, just to convert that to an unsigned long to make it smaller to save. I can say that there's another process now. So we have a new process count having another process that was added to the array, and I can return true indicating everything is fine. If I get to the end of this for loop and I can't get an empty slot, it means we're out of slots. That means that at least 32 processes have been created in fast, very quick succession before the first thread happened to be created already in those processes. So it's very unlikely, but for our purposes, it's going to be more than enough, so we can return false here as a way to indicate a failure, which means that we can also do some checks here. If this returns true, then everything is good. Otherwise, we can maybe have another DBG print that's saying that array is full. Again, unlikely, but still we can write it at least. It will be visible in a tool we're going to use. So this is add new process. And the problem with this code, some of you might have noticed that there's a problem with this code. And I don't have a poll question for that. But if you know what the problem is with this code, please type that in the chat maybe. What is wrong with this code, or what potentially is wrong with this code? I'll give you a few seconds to think about it. So you're right, there's a race condition here. There's something called a data race, and the problem is that this function could be called multiple times at the same time. You can have two processes or more created at the same time. or roughly at the same time. And so this function could be running concurrently on two different threads and two different processors even. And so what we have here is a data race. We're looking at the same data with more than one thread. At least one of them is making changes, and we are making changes here. This means we have synchronization issue here. And so it might work, but if we're unlucky, it won't work properly and we'll get into a mess, which means we need to synchronize. Remember that there's also the remove new process function, which is going to traverse the array as well. We also need to have a function to find the process ID in the list, which means we need to traverse the array again. So all these things would happen at the same time, and if we don't properly protect against it, we'll be in a terrible muddle, potentially blue screening the system, or at least having bad behavior from the perspective of trying to detect a remote threat. So we have to fix that, and the way to do that is to use some synchronization primitive to do that. And I'm going to use a fast mutex here. A fast mutex is a kind of mutex that's only available in kernel mode. I'm going to use a fast mutex because its API is slightly easier to use. Basically, it works like a normal mutex in the sense that only one thread at a time can acquire it. And so once a thread acquires it, if another thread tries to acquire it again because it tries to run the same kind of code or access the same kind of data, then it's going to block until the first thread releases that lock, that fast mutex, and the other one can grab it. So that's a way I'm going to work. In practice, it's actually not the best option here. It's a bit too pessimistic. And that's because in most cases, we'll do a find kind of operation here. And in the idea of find is that it's just about reading, only add new process and remove a new process are going to actually make changes. So there's a way to use something more efficient called an executive resource, which manages this idea of a single write and multiple readers. But the API is more complex. I'm not going to use that, again, to keep things as simple as I possibly can. So the first thing to do here before we actually use the fast mutex is to initialize that. So we have the initialize initialize fast mutex API here to just going to initialize that mutex to the free state, which means that any thread can grab it. And now we can use that in the code. So in the add new function, add new process function, I need to acquire the mutex. And this happens using the function x-acquire fast mutex, a very simple function. That's why I'm using that. Why I'm using it. And then, of course, I have to release it. So we need to use x release fast mutex. And if I do that in this way, we have, again, another bug here, a subtle bug, which we have to fix. And you might have noticed already the bug here if you're keeping track of all the stuff I'm doing here. And the bug is that if we add the process successfully, obviously, we're going to use return true here, and we're going to miss the release of the fast mutex, which is bad. It's going to cause a deadlock, and essentially our system is basically gone. It's going to deadlock, and that's going to be, of course, bad. So one way of dealing with that is to add that here or something like that, which is correct. It will work, of course, but there's a better way. One way to make it better is using something called a try finally block. This is called a termination handler, which guarantees that whatever you do in the try block, it's going to always run the finally block no matter what. It doesn't matter if you do return or go to or whatever, it's always going to invoke the finally block. This is one way of doing that. And if you're using just pure C, it's the only way to do that fully safely. With C++, you have one more option, but I'm not going to describe that again to keep things as simple as I possibly can. So once we have that in place, we have a new process here working for us. Okay, great. So when a new process is created, we're going to mark it as a new process. That's good. Now we need to deal with the thread creation. So obviously there's another bug error here. It just says that we're not using the process variable here. Again, I'm going to use unreferenced parameter here to make the compiler kind of happy, but still the application, the driver will not link because we didn't implement all the functionality. We didn't implement on thread notify. So let's go ahead and do that. So this is the main thing we want to really do. On thread notify is called when a thread is created or destroyed. And we can see there's a create boolean here indicating whether it's a create function or a destroy function. So obviously if a thread is destroyed, we don't care. We only care if the thread is created. So if it's not a create operation, we don't care. Because we just want to identify new threads being created, want to identify whether they are remote threads or not. So what is a remote thread? So what constitutes a remote thread? So the thing is that this function is called, and it creates this function is called because someone created a new thread, but that process is where the thread is actually going to be created in. So if the current process is not the same as this one, then obviously this is a remote thread. And so first thing we need to check is whether the current process ID, which fortunately is provided to us here by a function available in the kernel. If the current process ID is not process ID, then this is a remote thread for sure. However, that's not good enough because we know that the first thread in a process obviously is always a remote thread. So we need to kind of say that this thing is not really something we care about. We don't want to care about that. But let's start by looking at the basics there. A remote thread is a thread where the current process is different from the target process where the thread is about to be created. By the way, this little symbol here, don't get alarmed. It's the normal not like exclamation mark and equals representing not in C. I'm just using a certain font that has these nice ligatures that draws certain combinations in different ways. Don't worry, the C language hasn't changed while you were asleep or something. It's all good. There's another thing we have to make sure is that the process ID here, or the current process, is not the kernel process. So sometimes the kernel itself injects threads into user mode processes. It's not really documented, but sometimes it happens, and you don't want to deal with these cases. So if the process is not the initial system process, that's the kernel process, that's the process ID of 4, then of course we care about that. But if it is this kernel process, we don't treat that as remote. And then the last thing is also to look at the target process. If the kernel creates a process in itself, it really shouldn't be a problem, but let's just cover this case just in case. So it's basically process ID number 4. So it should be different. If it's different than process ID, still we're not going to deal with these cases. And this case actually is something that can't really happen, but I'm going to keep it here just to make sure. So if this is not a remote thread, then obviously there's no point in continuing. So we can just return. But if it is a remote thread, there's another thing we have to check to make sure it's not the first thread in the process. If it is the first thread, then it is not a remote thread after all. So the way to do that, we're going to look at the list of processes that we have. We're going to have a function called find new process with the process ID that we have. That's the process into which the thread is being created in that process. So if this is not found, or we can do the condition in one way or another. If it is found, let's start with that, it means that it is the first thread in the process, because the process is in our list. We just created the process, we added the process ID to the list, and we find it there. So if it's there, it means that this is the first thread in the process, which means that it is not a truly a remote thread, but we want to remove the process from the list. So if there's another thread created in that process from a different process, it will be identified as a remote thread. So I can do here, I'm going to say this is the process removed because first thread in process created. So that's why I'm doing that. It's not I'm doing that just for fun. I'm doing that because that's the first thread in the process. And now that we removed that process ID from our list, the next time a thread is going to be created in this process and this Boolean is going to be true, then we know it is truly a remote thread, which is right here. This is a remote thread. So we can see that this is really a remote thread. So I can use dbg print here. That's going to be the way I'm going to report that. Normally, in real EDR, I would probably report that to the service, to the user mode service, but here we're just going to use dbg print here. So we have remote thread detected. And so we have some PID and TID from the calling thread just for fun. And this is injecting into a new PID, some existing process, and that's the new thread ID. That's what I want to have here in my output. So the caller is PS get current process ID. That's our caller. That's the one that's doing the injection. So I'm going to use again handle to long to convert that into a 32-bit unsigned long. And then the same goes with the current thread ID. So it's something very similar. Handle to long. You can use the capital L or not. One is a macro, the other one is the inline function, the same thing. So we have thread ID here. That's going to be the original injector. That's going to be the injector process and thread. And then we have the injected process and thread. So we have handle to long, which is for the process ID we get as the target process, and handle to long with the target thread ID. That's the new thread that has been created. This is the injected thread. So I'm going to have this as a detection. The detection is going to be just a little print here. So that's basically it. Well, almost. We have to fix a few things here. We're missing remove new process. We don't have find new process. We have to implement all these things. Let's go ahead and do that. So let's go with find a new process. Of course, then we have the job of installing the driver and of course hoping I didn't have any bugs here, which is definitely not guaranteed. I might have bugs, who knows. So remove new process is going to be something very similar. I want to acquire the mutex here. Let me do some copy pasting here. I want to acquire the fast mutex, of course, to make sure that we don't mess up the data structure. We're going to look for the process ID. So we have handle to long here, and going to look for that process ID. If we find it, then the remove has happened. We're going to zero out that index to make that slot available and decrement the new process count, which means we succeeded. Otherwise, something went wrong and we're removing a process which we never added. So something really wrong is happening, but we don't care. We just return false and forget about it. So that was remove new process. And then we have find. That's our last thing here to implement, hopefully. So here's find, and again, it's going to be very, very similar. I'm going to do the same thing, basically, just doing some copy pasting here, and see if I can find this process. If I find it, great, I just return true, and I'm done. I'm not going to change anything here. I'm just looking for a particular process ID in my list. If I find it, I'm done. Otherwise, I return false, indicating I can't find the process. Okay, we're supposed to be done. Let's see. Let's build that. So it almost built successfully. There's a problem here with the linker again. And the problem is that the driver entry function has to be a C linked function, not a C++ function, which it is by default because I'm using a CBP extension here. I'm going to add an external C here to make the linker happy. So it finds the driver entry successfully. So now we're good. Everything compiles and links successfully. There's one other thing we have to do. If I go to the project and right click and go to the properties, there's one flag we have to add to the PE. So I'm going to select all platforms here, all configurations. If I want to then compile in release build or whatever, I want to do these things so I don't have to repeat myself. And if we go to the linker here, unfortunately, that option doesn't exist. Any of the available options here, we have to go to the actual command line edit ourselves. It's called integrity check. What that flag does, it adds a particular bit into the PE, which is checked by the kernel when loading a driver that uses certain APIs like PS set create process notify routine EX. So if I don't have that flag, the driver will fail to load. It will say something like access denied. So if you get this access denied, it's probably because you forgot to add that flag. Okay, so now we're really done. And we have here in x64, here's my debug version here, we have kdetect.sys, that's our driver. So I'm going to copy it and paste it into my virtual machine. In my virtual machine, already put here the injector and the simple DLL for that testing purposes. And now I've provided the sys file here. So the first thing we need to do is to install the driver, and then we need to load it up. So let's go ahead and do that. The first thing we actually have to do, which I've already done, is to put the system in what's known as a test signing mode. Because normally you probably know that kernel drivers can't be loaded unless they're signed with a proper signature. In fact, in today's systems, it's even more problematic than that. Actually, Microsoft has to sign your driver, not just you, even if you have a valid certificate for this purpose. And so my driver is not signed, and I'm definitely not going to send it to Microsoft. So I need to be able to test it, and that's the normal way of working. You can't really write a driver and just send it to Microsoft. You want to test your driver to see if it works. And so we can put the system into a test signing mode. This is done using a command line like this. It looks like this. You use bcdedit /set test signing on, and then restart the system. You need to do that once. So you do that, of course, from the administrator command window. Once you do that, the system is in this mode where you can install unsigned drivers. The next step is to actually install the driver. This also requires an admin command window. So here's an admin command window. And the way to install a driver, we don't have an INF file here, and we don't need it. In fact, it's not very useful here. An INF file is needed for certain kinds of drivers, like plug-and-play drivers that deal with hardware. But for other kinds of drivers, or some kinds of drivers, I would say, like this example that we're doing here, which is a pure software driver. It has no relation to any kind of hardware. It doesn't really care about hardware. We can install that just like we install a service. If you ever install a service using the Create Service API or using a tool such as SC, you can use it here as well. So SC can install a kernel driver as well, because it's about writing certain things into the registry. You just need to provide the appropriate parameters. So with SC, you can use SC create to install a driver or a service. I'm going to give it some name, like kdetect. The name doesn't really matter and has nothing to do with the actual file name. It's just going to become a registry key under a subkey called services. If you open a registry editor, you'll see that there is a location called HKey local machine system current control set services. Under services, we have a long list of keys, and these keys are about services and drivers. So drivers and services are installed under the same subkey. There's a reason for that. It's mostly historical, but doesn't matter for our purposes here. And so if this list provides information about services and drivers, how do we know which is which? And the answer is using this type value. The type value, if it's a small number like 1 or 2, it's a driver. If it's a large number like 16 or higher, 10 hex or higher, it is a service. So this example, this is a driver. This one is also a driver, type is 1. This is also a driver. And of course, we can find services as well. So this is an example of a driver as well. We can find services for sure. This is a service. You can see this is a driver as well. Let me find something like a service. This is a service. You can see the type is 20 hex. This is a service. And if you look at the services applet that you're probably familiar with from the controller panel and stuff like that, what we see here is the list of services only. There are no kernel device drivers here, just the services. So it's just like reading the entire set of keys there and filtering only on those where the type is 10 hex or higher. And so when I select here the kdetect name, it means that there shouldn't be a key here called kdetect. If there was such a key, the installation would fail. So I need to find something that doesn't exist. So kdetect is just a good name as any. You can choose any name that you want. And then we have to specify that the type here has to be a kernel, it needs to be registered as a kernel driver. So the type is going to be the value 1. So the way to specify that with the SC tool is using type equals kernel. Notice type equals has to be written without space in between, and then you have to have a space. So SC is kind of picky in the way you specify parameters. And then, of course, you need to specify where is the actual path to the sys file. If it was a service, that would be the executable of the service, but now we're installing a driver. It's going to be bin path equals, again, no spaces, and then one space, and then the actual directory, which in my case is etest and the kdetect.sys. That's the one. And I'm going to click enter here to create a service. So you can see it says success. Success just means that the service is supposed to be installed now. You can see that kdetect has been added to the registry, and the image path, the type is indeed 1. A start, by the way, indicates when this driver or service should start, and 3 indicates on demand, meaning only when you actually ask it to start. It's not going to start automatically when you restart the system. But of course, we could change that at the installation time or later on. And here's the image path, which is etest kdetect.sys, as we expect. There's a little prefix here, which you might be wondering what is all about, and I'm not going to explain that right now. But if you're familiar with the native, the way that the object manager stores information, then in the object manager namespace of the kernel, then you know that this is the symbolic link or the prefix for where the symbolic links are stored, and e: is actually a symbolic link. But that's not that important for our purposes. So you can see the driver is properly installed. It is not yet running. It's not yet running. In order for it to run, we have to do something to load it into memory. And to do that, we can use the SC tool again. It's basically calling the start service API function, which also is available to start services, obviously, but also can start these kinds of software drivers. In order to see some information about that, we can load or launch some tools. We can launch something like Process Explorer here. With Process Explorer, what we'll find is that there's the ability to see all the kernel drivers in the system. And one way to see that is going to the system process. When you look at the system process and look at DLLs, it doesn't really show DLLs, it shows all the kernel modules. And kernel modules are mostly drivers, but could be other entities. Basically, it's like kernel DLLs at the end of the day. So you can see here all the drivers loaded into this virtual machine. And of course, I'm using a virtual machine because I don't want to blue screen my system in case that the driver misbehaves. Maybe I have a bug, who knows? We'll have to check and see. So when we load the driver, we expect the kdetect.sys to be appearing right here. It should appear here, indicating that it is currently loaded. So I'm going to try it now. So first I've put here always on top as the option, so we see Process Explorer at all times. Let's go ahead and use the command start. So sc start is the command to start a service or a driver. And we need to give it the name of that registry key that we created previously. That, of course, is called kdetect. So here goes. There we go. So you can see that kdetect.sys has appeared. So our driver is loaded. It is, in fact, coming from the correct path, as we expect. The driver is running in the sense that it is in memory and has properly, hopefully, registered for the process of identifications. Of course, it must have, otherwise we would fail the loading and driver entry would return some failure value. So now, in order to see all the outputs that I mentioned earlier, how can we see that? So one way is to attach a kernel debugger to the system, which I'm not going to do here. Instead, there's an easier way. We can use a tool from sysinternals called debug view. I'm going to run debug view, and it's important to run it with admin privileges. This is necessary to see kernel output. And you can see here that already we see outputs for processes being created. And once the first thread is created as well, then that process is removed from our list, indicating that the next thread created in that process from a different process, that's going to be a remote thread. So we see this output. In order to see that, it's not automatic. You have to go to capture, use capture kernel here, and also enable verbose kernel output. These two options have to be checked to see this kind of output. Otherwise, you won't see it. And again, there's reason for all of that. The second option here, enable verbose kernel output, is necessary because by default, DBG print output goes down the drain, and you have to add some registry key to indicate that you'd like to see them by default. But debug view saves you from changing or to making that change into the registry by using this option, which basically causes the driver that DBG debug view has itself. The way that driver works is that it hooks the functions for outputs and then just grabs the output and sends it to its user mode application. So you can see that process get created, destroyed all the time. It's just the way things are. So let me create a notepad process here. So you can see that notepad has been created here and it's been reported. Just to prove that we can detect, hopefully, even the simple thing of debugger attaching to the process, we can do that as well. So let's try, even before we actually inject anything to Notepad. So I'm going to launch a debugger here, just like I did on my host system, and then attach to that Notepad. And now we expect this to be identified as a remote thread, because it is a remote thread injection once we do the output. But notice, by the way, that you get some other output here coming from the kernel or other kernel components. We can try to filter that by using a filter, but it's not going to be too noisy, so it's going to be probably fine. Let's go ahead and use attach to process again. We'll find Notepad, here goes. And once we attach, you can see that remote thread detected was shown here. Let me stop that for a moment. So remote thread detected. So we have detected remote thread execution now because of the debugger. That's how the debugger works. It injected a thread into process 6560, which is the process of Notepad, supposed to be. So here's Notepad 6560, that's the correct process ID. The injector itself is in process 1504. And 1504 is supposed to be the process of the debugger itself. So you can look for that. So 1504, I'm going to look by process ID here. You can of course use process task manager as well. So here's the process called ENG host. This is where the debugger engine is hosted when using the new WinDebug, the WinDebug X, the relatively new one that we have. Also, the thread that was created is thread ID 5984. The debugger says the thread ID is actually 1760, but that's in hex. So you can say 1760 and cross our fingers, and the value is indeed 5984, exactly as reported. So we see the report is in fact correct. Okay, good. So we can use like detach here, let Notepad continue running without a debugger. We don't need a debugger anymore. And now we want perhaps to use our injector to detect that injection using our application that we've written for this purpose. So I'm going to just try it as well. So I'm going to go to test. I have my inject here. Here's my injector. The process ID is the process ID for Notepad, which we already know, but I've already forgot the actual ID. So that's 6560. And I have my DLL here, which is called the simple DLL. Here goes. Let's do that. And so we get the message box here. I made a mistake. I forgot to continue the capture of the event. Sorry about that. So we have to do this again, but the DLL has already been injected, so we have to start with the new Notepad process, because the DLL can't be injected twice to the same process while it's still in there. So here's our Notepad again, but now Notepad, of course, has a different ID, so we need to find that new ID. So Notepad. So we have 13736. 13736, and cross fingers again. And now we can see remote thread detected. injected into exactly this process 13736. This is our notepad process. So there you have it. We'll be able to inject a thread into a target process, identify that by using a kernel debugger, which is definitely not something you see every day. But this is a powerful way to detect that, because you can't really bypass that. You can't bypass that kind of detection for create remote thread kind of call. Of course, it might be some different function like create remote thread EX and perhaps other variants like the native API, anti-create thread EX and things like that. It doesn't matter. And when a new thread is created, you get notification in the kernel, as there's no way around that from that perspective. That's one of the things that is very powerful as far as the kernel is concerned. Just to recap a little bit, just to talk about how we install a driver. This is the way to install a driver by using the SC tool with create, whatever name you want to give to that key. The type is kernel, and the bin path is where the driver binary is. In classic cases, the drivers are stored in the system32 drivers directory, but there's no requirement to store that in there. You can store them technically anywhere you want, and for our purposes, it does just is simpler to store the driver binary in some random location in the file system. So that's the demo I wanted to provide. If there are questions, since we think we have some time, so if you have questions you'd like to ask about that, I'm happy to answer anything that I can.
Okay, so there are many questions in the Q&A.
Okay, let me look at those questions.
Let's try to read them. Okay, so the first from Ravi. Sorry, I'm trying to translate it. How many drivers has registered for process creation or thread creation, module loading notification at runtime?
So I answered that as part of the talk there. So basically, you can't really tell how many callbacks you have. It's just there's no official way of getting that information. You just try it yourself, in the sense that you try to register your callback. If it works, great. If it doesn't, then tough luck, so to speak. There are ways, people have found ways to find that internal list and try to see who is actually registered and all that kind of stuff. It is undocumented, but it is possible to do if you do proper reversing. But in an official capacity, there's no way to get to that.
Another question by Yoav will be, why not to check the thread ID first?
So I guess that question was in context of the time when I demonstrated something, so I'm not sure I can answer that directly. But again, I'm trying to do some checks here, which I could definitely check, do the checks in a different order, but this is the preferred order that I've used here, and that's because it's the most efficient. Because calling file new process is a more expensive operation, so I want to use some basic heuristics to remove all the stuff that is unlikely, that is likely to be something I can remove very quickly without having to call any significant functions. All these checks are really very fast, just checking existing numbers.
Okay. So another question, will creating a new process and injecting into an existing thread of it theoretically bypass it?
So there's no meaning into injecting into an existing thread. What you can do is force another thread in a thread in an existing process to do your bidding. For example, by using an APC or something like that. And this is definitely more stealthy. It's a bit more complex to do, but it's definitely possible, and it will be more stealthy because there's no new thread being created, and so the driver has no special knowledge about that, and it's much more difficult to detect. And I've demonstrated that in one of my videos on my YouTube channel. You can look at that, how to force an APC to be run on a thread, or changing the thread context and pointing it to a different location to run some shellcode or some other function. Yes, this is stealthier. Definitely something you can do.
Okay. So Pavel, it seems that you have lots of fans here. I can tell you. I don't want to state out loud, but a lot of people love your presentation. Another question is, how do I reach that level of expertise to do that? Yeah, like to present what you're doing. Could you please recommend a roadmap start? Maybe it's like a career journey.
Well, that's definitely a question. Well,
Let me try to answer. First, I've shared a TrainSec link, so you have a link to more additional information and training and courses on TrainSec website, so you can go there and learn. And as a cybersecurity professional group, we also got a discount coupon. So I've shared it in the chat. Already shared it in the chat and also present it also in the end. So you can go and learn and have also a discount because you've joined our group. So it's a good starting point. But Pavel, if you have additional things that you want to add.
Well, it really depends on where you're starting from, but I would say my way of thinking is always start with the fundamentals. Because once you have good foundations, you can learn anything. I've seen people in the cybersecurity space try to learn how to penetrate things and do various stuff, but they don't really understand how an operating system even works. So you can't really reach any kind of significant level without starting with the foundations. That's one of the things I emphasize in my courses on TrainSec, like the Windows internals courses, other courses. It's really about starting with the basics. Doesn't mean it's simple, but it is foundational. Because once you understand the foundations, things are always changing. New features come from Microsoft, from other vendors. Things are always changing. But if you understand the foundation, it's very easy to catch up. You can read some kind of blog article or look at some video and you understand what is going on because you have the foundations. You understand processes, you understand threats, you understand scheduling DLLs, priorities, things like that that might be very important. So I would say for beginners, very important to start with the foundations. I guarantee it's going to bring you lots of benefits regardless of what you're actually trying to learn. Whether you're trying to learn kernel programming or even just normal Windows usable programming, or even if you're trying to learn math, it doesn't really matter. If you go with the foundations, later it's going to be much simpler. The other thing I want to give as a tip, which I always like to give, if you want to make sure you understand something, then go ahead and teach it. You don't have to teach it to like 1,000 people in some big giant ballroom. You can just teach it to your brother, your friend. Just talk to them and try to explain them. You'll very quickly figure out whether you understand what you're talking about or not. If you can't explain something in a simple manner, you're probably not understanding well enough, and you need to go back and look at that. So that's something I also recommend as a way to make sure you're truly progressing. Last tip I'm going to give you here is it's all about doing. You can read books, you can watch our video courses, you can watch anything you want. That's not enough. It's not nearly enough. It would give you some details, but you have to do the actual work. Once you do the actual work, whatever that work may be, if you're interested in programming, then go ahead and write some code. Then you'll find the real problems. Then you're really going to learn. It's always about doing. It's not good enough just to read or watch stuff.
For sure, just making Pavel's point even stronger. It's like a lot of people asking me, how do I become a great or a good reverse engineer or malware analyst? And I said to them, just download some malware samples and good luck. Just break your head, break your hands with IDA, with Ghidra, whatever. Learn assembly, learn stuff like this. Learn C. It's just a lot of doing. It takes a lot of time, for sure, for you to be an actual expert. And even then, you can't really name yourself as an expert because you always have to learn and learn and learn and learn. But as Pavel said, whenever you have the foundations, you're the real winner.
Another question here I see. So how much C do you need to know before signing up for malware dev course and other courses? So I would say you need to be comfortable with C. It means you need to know how to write functions, you understand pointers and structures and things like that. Don't have to be a super expert, but you do need to have the ability to write simple pieces of code and read C well.
Okay, those are great tips. So, by the way, you have here the coupon code. If you didn't write it down, so write it down. It's still valid. You can use it in TrainSec website. Moreover, this session recording will also be uploaded to our LinkedIn page. The slides would not be shared because it's proprietary of TrainSec. So if you want to receive additional information or more demos and technical stuff, you need to, register to the courses. You will have more than topics and more information related to how to build malware and do the malware research. That's over there. As I mentioned, it's proprietary of TrainSec, so just this session recording will be uploaded to our LinkedIn page. So if you're not a member, please be a member. So guys,
the code, by the way, just a little note here, Lior. The code will be available on my GitHub repository. I'll also send Lior the link later on once I upload it. So you'll be able to try it out yourself if you wish.
Okay, that will be very, very good. And of course, you can, contact Uriel and Pavel through TrainSec. Feel free to ask them questions. They will always find an answer, I can tell you for sure. They are very professional with what they are doing. So guys, if you have any further questions, please write them down in the Q&A. We finished a bit early, I know, but that's how we manage the time. We will have a spare free time. But guys, if you have any questions, please feel free to ask in the Q&A. We'll stay a bit more to answer, of course, all your questions. So let us know. Okay, thank you very much, Luan. Thank you very much. Okay, so thank you very much, guys. Hope you enjoyed. And as I mentioned, all the session recording will be uploaded to our LinkedIn page with Pavel unique link to his code repository or link to the code. I will be sharing it also in our LinkedIn group. So guys, thank you very much. Thank you, Uriel and Pavel, for very insightful workshop. It was very technical. I will need to learn a bit more. Okay, I'm a professional guy, but I will need to go into details, revised again what you've teach today, and maybe to take your course.
For sure. You're more than welcome.
Okay, guys. So thank you very much. Keep safe. Bye for all. Bye for now.
Bye, everyone.
Thank you very much. Bye.
God bless you.